Hey everyone, so this is Worksheet 10.7a, the video solutions, and we're going to be looking at solving trig equations, which we started back in section 10.2. So if you have any questions about some of the more basic ones we're doing here, you may want to go back and check out the 10.2 videos or notes. But we will be getting some trickier ones. So let's start with 1a. So we're asked to find values for x where the sign of x is equal to positive 1/2. Now in 10.2 we spent a lot of time looking for all possible solutions. In this particular case we're being asked to find only solutions between 0 and 2 pi. We're going to start by finding all possible solutions, and then we can whittle down from there to find just the ones that exist between 0 and 2 pi. Alright, but we'll start off the problem the same way as we did in 10.2. So we'll start by identifying the quadrants that we're interested in. So we'll say, well, when is the sign positive? Well, the sign's going to be positive in quadrant 1 and also in quadrant 2. So we at least got those. Then we're going to want to associate a reference angle in those quadrants. So we'll abbreviate that RA. Now the reference angle we put with the sign and positive, or 1/2 in general, is going to be 30 degrees. Or pi over 6. So now we can go into each of these quads and we can sketch our reference triangle using 30 degrees as a reference angle. So if we go into the first quadrant here, so this is quadrant 1, we draw our little 30-degree reference triangle. So that's 30 degrees right there. We know that this is the correct triangle because the hypotenuse, if we use our triangle of 2, 1, and positive root 3, the sign is the opposite over the hypotenuse, which would give us 1/2. So the angle that we've drawn here is 30 degrees, or pi over 6. So the solution we get from this one is pi over 6. And then if we go to the second quadrant to find our other solution, we draw our 30-degree reference triangle. So there's our 30. And we know 2, 1, and then negative root 3. So the sign of this will be, this triangle will be 1/2 as well. Now the angle that we're looking for is the one that starts in our initial position and rotates over to the terminal side there. This angle is 30 degrees shy of 180, or pi over 6 shy of a full pi. This is going to give us 5 pi over 6. So these are our two initial solutions in one full period of the sign of x. So let's go ahead and see what we've got. So x could be equal to pi over 6. And this solution is going to repeat itself every period, every 2 pi. So we account for that by putting on this plus 2 pi k, where k is an integer. And then our other solution is 5 pi over 6, which also is going to repeat itself every period of the sign, which is 2 pi. So we add on multiples of our period 2 pi. And again, we would say here that k is some integer, which we represent with that symbol right there, the double-barred z. Okay, now this represents all solutions. So these are all solutions to our equation. We only want the ones between 0 and 2 pi. So our technique is going to be, well, let's start to plug in different k values and see which angles pop out that happen to fall in this interval. There are a couple techniques that we can use. First, it really would not make sense to use negative k's here, because the minute we start plugging in a negative k, we would see that the resulting angles would come out negative for x, which would not be in our solution interval. If we used k equals 1 for these two, we would be taking a positive angle in both cases, adding 2 pi to it. So that would push us out of the other side. So we don't want anything negative. We don't want anything equal to 1 or greater. So really our only possibility here is to try k equals 0 first. So if we let k equals 0, let's see what happens. Well, we get x equals pi over 6 plus 2 pi times 0. This is going to give us pi over 6. And then for our other set of solutions, we've got 5 pi over 6 plus 2 pi. We let k be 0, and we get 5 pi over 6. these are going to be the only solutions here. So we take these and we say that so x must be equal to pi over 6 or 5 pi over 6. And again, if you don't want to take my word for it, you can try letting k be something else other than 0 in this case. And you'll notice that those solutions are going to fall outside of the restricted interval we've been given in the directions of this problem. So this is going to be our answer for 1a. Now we get a similar problem in part B, except notice that now we have the sign of 3x is equal to 1/2. So that coefficient, if we remember from 10.5, that coefficient from the x is going to affect the period. And that's going to affect the number of solutions that we have from 0 to 2 pi. We'll see that as we go through this problem. So here's a trick that we can use to simplify this problem. Rather than using the 3x, let's let 3x be substituted out by using a u. And it's going to make this problem seem a little bit more familiar to us. So now what we have is we've got the sign of u is equal to 1/2. Now, if we think about this, this looks a lot like the last problem that we had here, which was sine of x equals 1/2. So we can take, we could do it now. We could run through all this work, or we could use the work that we did in part A, and we can say that we know as we work through this that u is going to be equal to pi over 6 plus 2 pi k, and u is going to be equal to 5 pi over 6 plus 2 pi k. So we're just saving ourselves a little work here. Now, that's all well and good, but we wanted to solve for x. So we need to remember here that u is 3x. So we're going to plug back in our 3x here, and 3x could be pi over 6 plus 2 pi k, and 3x could be 5 pi over 6 plus 2 pi k. Now we solve these for x. And we would do that by dividing both sides by 3. So we'd get x is equal to, if we take pi over 6 and divide by 3, we'll get pi over 18 plus 2 pi divided by 3 times k, and x is equal to 5 pi over 18 plus 2 pi over 3 times k. And again, what we have here, these are all solutions for part B. We want solutions between 0 and 2 pi. So we're going to take the same approach that we did that turned out to be sort of trivial in the first one, which was let's start plugging in different values for k and see what angles we get coming out of this. So to find solutions on the interval from 0 to 2 pi, or for any interval for that matter that you're given, we're going to test various integers for k. Alright, so we're going to do that now. So let's start with k equals 0. That's always a nice place to start. So if we let k equals 0, we're going to get x is equal to pi over 18 plus 2/3 pi times 0, and we're going to get x is equal to 5 pi over 18 plus 2 pi over 3 times 0. And what we'll see here is that the values that come out are just our initial angles, so pi over 18 and 5 pi over 18. Now, are those angles between 0 and 2 pi? Well, here's something that I sometimes like to do to kind of keep as a check, is our interval is from 0 to 2 pi, all of our solutions are going to come out as fractions with an 18 in the denominator. Let's write this interval so it makes it a little bit easier to see in terms of that. So 0 is the same as 0 pi over 18. And 2 pi is going to be the same as 36 pi divided by 18. So we want to find solutions in between these two. So we've got 1 pi over 18, that checks out. 5 pi over 18, that checks out. So now we can go from there. Okay, so k equals 0 works. Now let's go to k equals 1. So if we let k equal 1, we're going to have 11 pi over 18 plus 2 pi over 3 times 1. Now we're probably going to make a common denominator here. So this is going to give us pi over 18 plus, we're going to multiply top and bottom by 6. It's going to give us 12 pi over 18 there. And this is going to give us 13 pi over 18. And then we'll try with the other solution. So we'll let k equal 1 for the second one. And we'll have 2 pi over 3 times 1. That's going to give us 5 pi over 18 plus 12 pi over 18, which is going to give us 17 pi over 18. Both of these also happen to fall in between our solution interval that we're looking for, between 0 pi over 18 and 36 pi over 18, or 0 and 2 pi. All right, so good news, bad news, we get to keep going. So now we'll let k equal 2, see where this gets us. So if we let x equal pi over 18 times 2 pi over 3, we're going to multiply this by k equals 2 now. I'll set up both of these first. So 5 pi over 18 plus 2 pi over 3 times 2. Okay, so the first one we're going to have pi over 18. 2 pi over 3 times 2 is going to be 12 pi over 18 times 2, which is going to give us 24 pi over 18. This is going to give us 25 pi over 18. And then we'll have 5 pi over 18 plus 24 pi over 18. And that's going to give us, what, 29 pi over 18. Both of these are solutions between 0 and 2 pi, so we're going to keep them. And we just kind of have to keep on going until we leave our interval. So let's now let k equal 3. Okay, so we've got x is equal to pi divided by 18 plus 2 pi over 3 times 3, and then x is equal to 5 pi over 18 plus 2 pi divided by 3 times 3. Okay, good news here. So notice that if we multiplied our 2 pi over 3 times 3 in both these cases, we're going to get pi over 18 plus 2 pi and 5 pi over 18 plus 2 pi. These are clearly going to fall outside of our interval that we're looking for between 0 and 2 pi, because we're taking 2 pi and adding positive angles to it. So these are not going to work. These are going to be greater than, both of these are going to end up being greater than 2 pi. So that's good news for us. So we don't have to do any more k's in the positive direction. We can stop there. Now we might want to consider negative k's, but in this case what we'd be doing is we'd be subtracting angles from our initial angles that were larger than the initial angles, and we end up with negative values. So I'm just going to kind of make a note of here that if we let k be negative, x would be less than 0. So we don't want those, and you could test those if you want to. So we've finally got our solutions here. So these 6 right here are our solutions. So x could be pi over 18, 5 pi over 18, 13 pi over 18, 17 pi over 18, 25 pi over 18, or 29 pi over 18. These are the possible solutions between 0 and 2 pi to our original equation. Okay, so these, when you've got this multiple in front of our x, this is going to tend to be the situation where you have to run through these k values to find all the possible angles that you work through. But what I would suggest you do is start by doing this little u sub that we did. It seems like forever ago now. Then we got our initial solutions for u. Then we substituted back in our 3x, what we substituted out, and we get all solutions. Then the last step is go and we find all solutions on our interval by testing various integers for k. Okay, that was a doozy. All right, so now part C. Wow, this looks like a real treat now, finally, after doing that last one. So this is a lot like what we did back in section 10.2. So we've just got the cosine of x is equal to the square root of 2 over 2. So as before, let's consider our quads. So what quadrants are we going to look for solutions in? Well, the cosine is positive in quadrant 1 and in quadrant 4. And then the reference angle, which we associate with the cosine in root 2 over 2, is 45 degrees, or pi over 4 in radians. So if we sketch these solutions, so we'll start with our first quad. So we draw out the first quadrant. We draw our 45, 45, 90 reference triangle. So there's our reference angle of our reference triangle, 2, root 2, root 2. And since we're in the first quadrant, our angle is just that reference angle. So one possibility is pi over 4. If we draw our fourth quadrant solution now, sorry, I should have put arrows on there. So now we draw our fourth quadrant solution. So we draw our 45-degree reference triangle. So there's the 45 degrees. We've got 2, square root of 2, negative square root of 2, because we're in the fourth quadrant here, whereas here we were in the first quadrant. Now, what is this angle? Well, the angle, we start at 0 and we rotate through into the fourth quadrant. So the actual angle solution here is going to be 7 pi divided by 4. These are going to be the only two angles that we have between 0 and 2 pi. Again, if we wanted to, we could consider all possible solutions. So all solutions, we would take x equals pi over 4, and we'd add the period, which is 2 pi k, and we take x is equal to 7 pi over 4, and we'd add the period, 2 pi k. Now between, oh, and again, k needs to be some integer, and you want to specify this because k can't just be anything. It's got to be an integer. So between, actually, rather than say between, let's say on the interval from 0 to 2 pi, which is really what we're after here. The only one that would work would be k equals 0. So only k equals 0 works. Anything negative would give us a negative angle. Anything greater than 0 would spill out of our interval from 0 to 2 pi. So we'd only get x is equal to pi over 4 and 7 pi over 4. Okay, so not too bad. And then part D, again, pretty familiar one. The quadrants, we'll do that first. So cosine is negative in quadrant 2, and it's negative in quadrant 3. Again, the reference angle we associate with the cosine and root 2 over 2 is 45 degrees, or pi over 4. So now we're going to go ahead and we're going to draw our reference triangles in the second and the third quadrant for this one. So when we go over to the second quadrant, we draw our 45 degree reference triangle, 2, root 2, negative root 2. Our angle of rotation in this case is 90 degrees plus 45, so 135 degrees, or in terms of radians, it would be 3 pi over 4. So that's our second quadrant. Now if we do the third quadrant, down here, we draw our 45 degree reference triangle. That's 45 degrees right there. Got 2. Now both of these sides are negative. And our angle of rotation starts at 0 and goes into the third quadrant. So that's going to be pi plus pi over 4, or 180 degrees plus 45 degrees. That's going to put us at 5 pi over 4. And those are the only two solutions we have from 0 to 2 pi, are those two. So much in the way that we justified it last time, x, or back in part C, the only two solutions from 0 to 2 pi here would be 3 pi over 4 and 5 pi over 4. And that's going to be usually going to be the case if we don't have a coefficient in front of our x for sine and cosine. We would just look at the natural period of that function between 0 and 2 pi, and those are only two we've got to worry about. Okay, part E, we have a little something different here. So we've got the cosine of negative x is equal to the square root of 2 over 2. Well, we're going to dig deep into our identity toolbox, and remember that there was a set of identities we talked about in section 10.4. So recall from 10.4 the even and odd identities. So the even odd identities. And for the cosine, it said that if we've got the cosine of negative x, this is going to be equal to cosine of x, because the cosine function is an even function. So we've got this property where if we take the cosine of a negative angle, it's going to be equal to the cosine of that same angle, except the positive version, and vice versa. So we can actually use this pretty handily to consider, well, this is just telling us that we're trying to find the cosine of positive x for being equal to the square root of 2 over 2. And we have already done this. We have no need to do this. This was back in part C. We know that x could be pi over 4, or x could be 7 pi over 4. So we already did the work for that, so I see no reason to do that again. All right. So, you know, a justification for knowing your identities. Sometimes they can make these problems work a lot more easily. Okay, and F. So we've got the cosecant of x is equal to 0. So let's think about what this is asking for a second. So this is saying, when is the cosecant equal to 0? Now we know that when we're asking when is a function equal to 0, this is essentially asking us for x-intercepts. And if we keep in mind the cosecant function, we know that there are none. Let's do a quick sketch just to justify this. The cosecant is the reciprocal of the sine function. And if we were to graph it, so we've got asymptotes at 0, pi, 2 pi, negative pi, minus 2 pi, and our curve looks something like this. We just sort of get these alternating u's in between the asymptotes. Now notice that these curves never get between 1 and negative 1. So does this curve ever hit the x-axis? No. So there are no x-intercepts. And because there are no x-intercepts, this implies that the cosecant of x never equals 0. So we would just go ahead and claim for this one, since there's nothing we could put in for x that would make this function equal to 0, there's just no solution. Those are the best. No more work. Okay, so we've got that done. Now, part G. So we've got the tangent of 2x minus pi. All right. The approach that we're going to take with this one is not unlike what we did with the sine of 3x is equal to 1/2 back in part B, is that the prospect of working with that 2x minus pi just is not something I'd like to do right now. So what we're going to do is we're going to do a quick substitution, and we're going to let that 2x minus pi be equal to u, and then sort of proceed from there. So this tells us, I'm going to stick with green for these, that the tangent of u is equal to 1. So let's just solve this for u. So when is the tangent equal to positive 1? Well, if we were to graph this, and I'm going to put this all on one set of axes. Now keep in mind, the period of the tangent is pi. So these solutions are going to repeat themselves every pi, as opposed to with sine and cosine, they repeated themselves every 2 pi. So one solution here is going to be in the first quadrant, this 45-degree reference triangle. So we've got 2, root 2, and root 2. So we see that the tangent of pi over 4 is equal to opposite over adjacent, which is equal to 1. So one of our solutions is going to be x equals pi over 4. Now since the tangent has a period of pi, as I mentioned before, these solutions are going to repeat themselves every pi. So there's actually going to be another one 180 degrees away right here. If we were to rotate pi, we would have another solution in the third quadrant. And then we could go from there. We'd end up back in the first quadrant, and we'd keep rolling around and hitting solutions every pi. So as opposed to the sine and cosine, which need 2 solutions over the course of their period, the tangent's just going to have the 1. So our solution can be written as x is pi over 4 plus the period times k, where k is some integer. So we only need the 1. If we added the other one in the third quadrant, we'd end up with redundant solutions. So that's why we do that. And again, pi is the period of k, of tangent. Okay, so that's all well and good, but but unfortunately we didn't want a, oh, I'm sorry, this was for u, right? So we've got u. U is equal to pi over 4 plus pi k. We wanted to solve for x. So we make our substitution for u, and we're going to get 2x minus pi is equal to pi over 4 plus pi times k. And now we want to isolate our x here. So let's do that. So we'll add pi. So we'll get 2x is equal to pi over 4 plus pi k. So 2x is equal to 5 pi divided by 4 plus pi times k. And then we'll divide both sides by 2, and we'll get x is equal to 5 pi divided by 8 plus pi over 2 times k, where k is some integer. So again, these are all solutions. We just want the ones between 0 and 2 pi, which means we have to do this testing k technique again. So now we test k's, or different integers. So let's see. If we were to let k equal 0, that's a good starting place, right? So if we let k equals 0, what do we get? We get x is equal to 5 pi divided by 8 plus 1/2 pi times 0, which is just going to give us 5 pi divided by 8. Now, does this work? Well, let's double check. Let's do what we did last time with this. We consider our solution interval, which is from 0, come up here, 0 to 2 pi. Looks like we're going to have 8 as our denominator for this, so we'll write this as 0 pi over 8 to, what, 16 pi divided by 8. And that should be a parentheses in that first one, around the 2 pi. All right, so we want all solutions between 0 pi over 8 and 16 pi over 8. 5 pi over 8 clearly fits that one, so we're going to keep that. All right, so now we'll let k equal 1. If we do that, we'll get x is equal to 5 pi over 8 plus pi over 2 times 1, which is equal to 5 pi over 8 plus, so that's going to be 4 pi over 8, and that gives us 9 pi over 8. And that's a solution as well, so we'll keep that, and we keep on rolling. So we let k equal 2, and we're going to get x is equal to 5 pi over 8 plus pi over 2 times 2, which is going to give us 5 pi over 8 plus, so that's going to be pi or 8 pi over 8, which gives us 13 pi over 8, which works. And if we let k equal 3, we get x is equal to 5 pi divided by 8 plus pi over 2 times 3. So let's see, that gives us 5 pi divided by 8 plus 3 pi over 2 is going to give us 12 pi over 8, which gives us 17 pi over 8. Now if we double check here, 17 pi over 8 is outside of our range, so we are actually going to ditch this, and we can stop increasing k's. So we've got 3 solutions so far. Now let's see what happens if we used k equals -1. We should always check. We don't want to dismiss it. Let's see if we let k equal -1. If we let k equal -1, we would get x equals 5 pi over 8 plus pi over 2 times -1. That would be 5 pi over 8 plus a -4 pi divided by 8, which would give us pi over 8. So does that work? Yeah, pi over 8, that's a positive angle, so we actually have to keep this one. So in this case, negative angles are actually working. It's not going to go any further than that. If we let k equal -2, then what we'd end up with is we'd equal x is equal to 5 pi over 8, and then we'd end up minus pi. If we multiply by -2, this number is going to be less than 0. So we don't want this one. All right, so in terms of all of our solutions here, we've got, I'm not going to rewrite these, I'll just go ahead and I'll circle these in blue. So all of our x's are this, 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 and this. So we've got 4 possible solutions here. Okay, so that was a tough one, but kind of gives us the idea of how we go through and test these k's. And again, we really only end up having to do this when we start getting trig functions where that argument inside is something more complicated than x. That's where we really have to do this process of testing these k's. Okay, last one, h. So we've got the sine of 2x is equal to sine. So lots of times when we get these problems where we have more than one trig function floating around in here, we've usually got to use other techniques to solve this rather than just going straight to our reference angles and reference triangles. One way is we could try and sort of think of it as an algebraic expression, but in this case we're going to want to use trig identities to help us solve this. So we've got, let's think about our trig identities. And there's no guaranteed way to approach these. Sometimes you just have to troubleshoot and think of possibilities. If we did use trig identities, one thing we can think of is the sine of 2x. This is the double angle identity. So using the double angle identity, and this is from section 10.4, and we're using that on this, we know that the sine of 2x is actually going to be equal to 2 times the sine of just x times the cosine of x, and that's equal to the sine of x. Now we are going to use an algebraic sort of approach for this in that we've got 2 terms, sine is common to both, so we're going to move everything to one side, set it equal to 0. So we're going to get 2 times the sine, and I'm going to drop the parentheses, sine of x times the cosine of x minus sine of x is equal to 0. Sine is a common factor to both of these, so I'm going to factor out a sine. That's going to give me sine of x times 2 cosine x minus 1 equals 0. What this allows us to do is we are able to set up 2 different equations that just have one trig function in them, just sine or just cosine, and we know how to handle those. So now we can break this up. So since sine of x times 2 cosine of x minus 1 equals 0, either the sine of x has to be 0 or 2 times the cosine of x minus 1 has to be equal to 0. This means if we solve this for cosine of x, we get cosine of x is equal to 1/2. So now we solve both of these. All right, I'm going to label these 1 and 2 just so we can handle them in order. So the first one that we're going to do is sine of x equals 0. Well, the sine is equal to 0 on the x-axis. So on the x-axis. So our two solutions here are going to be x equals 0 and x equals pi. There are no other solutions between 0 and 2 pi, if we're not including 2 pi. So those are our solutions here. And then for part 2, we've got the cosine of x is equal to 1/2. And I will spare you all the work for this, but I think you know how to do this at this point. You identify the quads, you identify the reference angles, and if we did this, we would get x is equal to pi over 3 and 5 pi over 3. Those are the two solutions there. And we want to double check these. We could plug them both back into our original equation. And if we did check both of all of these solutions, so let's go ahead and write that because it is good to do this. We want to check these in the original equation. If we plugged in 0 to our original equation up here, that would work. Pi, so the sine of pi is equal to the sine of 2 pi. That's definitely true. They're both 0. The sine of pi over 3 is equal to the sine of 2 pi over 3. And the sine of 5 pi over 3 is equal to the sine of 10 pi over 3. So all of these work. So x could be equal to 0, pi over 3, pi, or 5 pi over 3. And these would be the solutions to this one. Okay, so lots of good practice with this one, and that should do it for this set of solutions, and I will see you all in the next video.